Thanks for that nice introduction, Tim. I think that then I'll just dive right into it, and you'll know a bit about me already. Okay, so Treble Technologies is a startup, as previously mentioned. Technically, we're a software startup. We're building software, but obviously this software has a lot to do with sound. So we're a sound and acoustics startup as well. I would like to start with just briefly telling you the backstory of the company before diving into the technical details of what we're building. So the company was founded in 2020 by me and Jesper Pedersen. We are a couple of acoustics engineers. We met actually when we were studying acoustics at DTU, what was it, 2011 to 2013, and studied together our masters in acoustics then. After that, we sort of went a bit our separate ways. I went into the building industry and was working as an acoustic consultant for a few years, doing lots of primarily room acoustic simulations, a bit of environmental acoustic simulations too. Jesper went more into the sort of product industry. He was working in a hearing aid company called Oticon for many years, a simulation specialist there. So him and I both kind of doing lots of sound simulations. And I then got the opportunity to go back to school to do a PhD at DTU to kind of continue the work I had done in my master's on sort of developing new technology to simulate sound and acoustics. And during this PhD, I was very fortunate to get to work with some very prominent scientists, both in the field of acoustics, but also within sort of computing and simulation science and so on. And through this sort of interdisciplinary collaboration, we managed to build some sort of prototype of a new simulation solver or technology that was very promising. So then by the time I was finishing the PhD, I called my good old friend Jesper and said, hey, I have this pretty cool prototype of some new simulation technology. And, you know, you and I, we know both a lot about sound simulation. Should we maybe try and build the company around this and build this into a real product and try to get it to market to enable people to work better with sound simulation? And that's how it started. We started in an empty windowless basement at the University of Iceland, where we got to be for free. But since then the ball kind of started rolling, and we started to get some interest from different companies and so on in what we were doing, and have been managing to grow the team quite a bit during this time. Gunnar and Ingimar here, they also kind of came almost from day one. Gunnar is sort of more leading the business side of the business, and Ingimar is sort of pure software developer leading the software aspects. So now we have grown to close to 30 people. This is a bit of an outdated photo because quite a few people have joined since this time. It's a mixture of acoustics and audio specialists, software engineers, machine learning specialists, and kind of, let's say, entrepreneurs or sort of commercial people as well. And we are based in Reykjavik, Iceland, out of all places. Right now in Reykjavik, there's like a crazy snowstorm actually. So I'm kind of looking forward to the winter getting over, but still it's not too bad here. Okay, Treble itself, the product we're building, we typically talk about it as a platform of virtual sound, meaning it's a software package that has functionality relating to sound simulation on the one hand, which is this concept of having a 3D model of something and being able to simulate how sound is going to behave in that 3D model. It can be a model of a building or a particular space within a building. It can be a model of a car, or it could even be a model of some sort of device like a loudspeaker, things like that. And then on the other hand, we have functionality relating to sound rendering or auralization, which is the concept of being able to not just get out some graphs and numbers that tell us what the acoustics of this meeting room is going to be that I'm simulating, but how is it actually going to sound so I can listen to it, and preferably in some sort of immersive, interactive way where I can move around, I can change some settings on the fly and kind of experience the difference, and also then use this to communicate acoustics designs to stakeholders, maybe people who are not experts in acoustics, and you know, graphs about acoustics don't mean much to them. When we started the company, we were very much thinking about the building industry. We wanted to build a simulation product that would enable architects and engineers in the building industry to better work with sound, to have sound be kind of more integrated into the building design process by having a seamless software product that kind of links into 3D modeling tools that people are using and can enable them to easily evaluate the acoustic quality of their design, listen to it as well, and do that in a sort of precise manner as well with some of these new simulation technologies. This certainly still remains a very important part of our sort of target market, but we sort of quickly realized as we got going that being able to simulate sound in a fast and efficient, precise manner in a kind of modern software package has use cases beyond just building design. So we worked quite a lot in the, I don't know if we call it the tech space or audio equipment space as well. Mostly sort of thinking about simulating the interaction between some sort of device and the space it is placed in, and doing some optimizations of audio equipment with respect to that, or even the common use cases that people are simulating in bulk, simulating a lot of rooms, simulating devices in lots of different scenarios to kind of generate data sets to be able to train some audio processing algorithms, some machine learning based processing algorithms based on these kind of high quality data sets. Automotive, we have sort of started to dabble in that field, have worked with a couple of big names in that field to try and simulate the acoustics of car cabins and the interaction between a sound system and a car and so on. And then this last part here, metaverse, which is of course a very vague term. No one really knows exactly what it is, but our interpretation is, you know, we're talking about some virtual environment where we want to have a realistic sound experience. Okay. When we sort of pitch the product or the technology itself, then we typically emphasize these three main points that we are trying to bring to the table with this product. First of all, which is perhaps the core of it all, is that we're trying to introduce a new type of acoustic simulation technology, which enables more precision and or more speed compared to what has been kind of commercially available up until now. And I'll talk quite a bit more about this when I go a bit deeper under the hood in a second. Then we're combining this with a kind of rather strong emphasis on a, let's say, modern, seamless workflow. So for example, we integrate this software technology into 3D modeling tools and gaming engines and things like that that people are already using to try and make the whole process very seamless. And then it's all kind of web-based and cloud-based, so you don't have to install any software on your computer, and it's very scalable. You can run thousands of simulations in parallel if you want, then all your history is backed up, and these kind of nice things that come with working in this way. Excuse me, 1 second. Okay, and then last but not least, because we can simulate sound in a rather precise way, then we can also generate perceptually authentic sound rendering experiences or listening experiences. And as mentioned before, try to couple the visual aspect and the audio aspect together and have it interactive in some way. The current overview of this platform we are building looks something like this today. I will show you a demo of this thing later, as previously mentioned, of the beta version. But there's kind of the centerpiece of this platform is this web client, which is a user interface where people set up simulations. They can assign materials and sound sources and receivers and settings and things like that. This ships to the cloud, which does the number crunching itself, and then results come back here where people can both look at the graph of numbers and also do these kind of immersive listening experiences in the model here. And we then have this sort of live link connection to a couple of well-known 3D modeling tools between the 3D model tool and this thing. So there's no kind of import or export of files or things like that. This is what we currently have. If we look a bit into the future for the plan or the roadmap for the next year or two, then there are kind of a few things we are planning. We're building integrations into gaming engines, enable kind of coming in from that perspective and use the simulation technology to generate some listening experiences. We're also building a sort of API product or an SDK product which allows people to kind of take and work directly on a sort of more programmatic level with the simulation technology. And then adding support with more 3D modeling tools. These are sort of some of the things that we are planning to do in the next year or so, or are working on for the next year. Okay, this is a snapshot of the tool, but as mentioned, I will give you, I will just open up the tool in a second and show you how it looks. So I'll skip ahead here. That was kind of the broad overview of Treble as a company and and about this product or platform that we are building. I hope it makes sense. But now we'll dive a bit deeper into the technology itself and sort of some of the research that lies behind, and then show you some benchmarks and examples and things like that as well. Okay, so our approach to simulating, primarily we've been thinking about room acoustics up until now. We have been doing some vibroacoustics and things like that, but that's more in a prototype stage at this point. Also environmental acoustic simulations, but so primarily we're working with room acoustics, and then sort of also this, as mentioned before, this interaction between device modeling and room acoustic modeling together. And then our approach to this is an approach which has been known for many years, and people have you know, especially maybe in academia, done all kinds of implementations of this, where we have a wave simulation at lower frequencies and then geometrical acoustics at higher frequencies. For smaller spaces, let's say meeting rooms, residential areas, things like that, we can use wave-based only for the full spectrum. But when we go to larger spaces like auditoriums or concert halls and so on, then this becomes quite heavy to cover the full spectrum, and therefore we kind of combine these two approaches. Wave-based methods, they have the benefit of being very accurate. There we are kind of solving the differential equations that describe wave motion, but the drawback is that as frequency grows, the compute time grows quite a bit. Geometrical acoustics, on the other hand, is kind of a rather fair approximation at high frequencies. It is essentially a high frequency approximation, but the accuracy can suffer, particularly in cases where wave phenomena is prominent, which happens more at the lower frequencies. So as mentioned, this concept is maybe not new as such, although there may be not many commercially available packages that offer this. But sort of our main pride is actually this wave-based solver that we have built, and that is very efficient when we benchmark it against numerical simulation tools that are available, like COMSOL or ANSYS or those types of tools. And we find that it is something in the range of 100 to 1,000 times faster than those types of solvers. And that speed up is attributed to two things. First of all, we're using kind of some modern numerical methods that are very efficient, and I'll cover that in a second. And then kind of combining those methods with the power of the cloud, running on massively parallel computing architectures. And this enables us to do very efficient, precise simulations. The numerical method that we rely on is called the discontinuous Galerkin finite element method. This is a sort of flavor of a finite element method that has certain attributes which are attractive for acoustic simulations. First of all, like many numerical methods, like boundary element methods and regular finite element methods, it has a high level of geometric flexibility because it can work with these unstructured meshes, so we can rather precisely simulate complex geometries. But when we combine that with the method's high parallel efficiency, that's sort of this kind of combination of these two factors is what makes it so attractive. So we can do complex geometries, and it's very efficient to parallelize. Finite difference time domain methods, which some of you might be familiar with, they have a very high parallel efficiency, but they don't have this level of geometric flexibility. So this method kind of has best of both worlds in some sense. Of course, there are many different numerical methods out there, and they all have their pros and cons, and I'm not necessarily saying that this is the holy grail or best method for everything. It's going to be problem dependent and all that, but we at least like this one quite a bit. Then in addition to these kind of two main factors, it's easy to extend this method to high order accuracy, which, long story short, means that we can do more efficient simulations. We can rely on higher order basis functions when we represent our solution in this computational mesh. And it has a lower memory footprint than traditional finite element methods, considerably lower. So I've kind of tried to illustrate here the difference between traditional finite element methods and the discontinuous one. In a traditional finite element method, when you've discretized your domain, the thing that you want to simulate on, then you end up with a mesh of kind of these small elements, and they're all interconnected. And that makes it difficult to parallelize this in a very efficient manner, because kind of the solution here influences the solution in all other elements. In discontinuous formulations, then each element is sort of semi-independent of all other elements, so we can kind of solve them all in parallel, and then just do a little bit of communication between elements, between time, if it's a time domain simulation, then between time steps in our simulation. And that's what makes it so parallelizable. Okay, and then combining this as mentioned, combining this numerical method with the power of the cloud, so we really kind of exploit this this parallel efficiency, is what makes the whole thing quite attractive and interesting. And as mentioned here, DGFM is well suited for parallelization due to this independence of elements. So the way this works in our implementation is that we have a room here. This is a simple box-shaped room, and we divide this room into subdomains. And in our implementation, each subdomain is handled by a single CPU core, but this CPU core is linked to a GPU, which has thousands of cores. So each element in this part, or in this subdomain, can then be solved in parallel on the GPU, and only some very minimal communication between elements here needs to take place, and only between CPUs here at the sort of boundary of this, this subdomain. I will show you at least one example of sort of performance numbers and scalability numbers a bit later in the presentation. We have spent a lot of effort on developing all kinds of technology, or let's call it physics components in our simulation stack, and I will cover here a few of these. First of all, relating to modeling of surfaces. So as we all know, the acoustics of whether it's cars or buildings or whatnot, they are greatly influenced by the materials, the sort of boundary properties or surface properties of the materials in the space. And we can model, when we do wave-based simulations, then it kind of opens up opportunities to model boundaries in a more precise manner than in traditional geometrical acoustic simulations. So we can model the surface in terms of impedance, which means we both model the absorption and the phase shift at the boundary. We do, however, also support sort of traditional absorption coefficient, energy-based absorption coefficient inputs as well. And then we have developed some technology to convert those absorption coefficients to surface impedances. It's kind of trying to guesstimate, if that's a word, what the surface impedance will be for a given absorption coefficient curve. And this is kind of originating in research coming out of DTU. For certain types of materials, we can also model them even more precisely than just using the surface impedance. We can model what's called the extended reaction of porous materials, which means that we can model essentially the sound field inside the porous material and how that interacts with the sound field in the domain or in the air. And this means we can kind of capture the sort of angle-dependent behavior of the surface, which can, in certain cases, have a significant impact on the acoustics. This is a whole field within on itself. I'm just kind of very touching the surface here, but mentioning this briefly. Sound source modeling is another field within on itself. We have done some interesting work in this, but also have some exciting stuff in the pipeline, I will say. So obviously doing omnidirectional point sources is kind of the most basic thing for sound source modeling. Surface sources is also something we have been working on. So you could have kind of a geometry of a loudspeaker, for example, and then excite like a membrane on like in like a real loudspeaker does, and then this kind of captures the directivity of the loudspeaker by having the box around and everything in the simulation. And then these are some benchmarks we have done here, where we see that we can in a pretty decent way capture the directivity pattern of a given loudspeaker box with this approach. But then right now we're working on some very interesting stuff, I think, where we're taking an arbitrary directivity pattern of some sort of sound source and can fit that to a spherical harmonics model and excite the simulation with this. Then we can kind of model any sound source that we want without having to model the geometry of it. We've also been doing a lot of work with sort of, let's say, the receiver side. So capturing the simulated sound field in a very precise manner to be able to either create binaural listening experiences or just analyze the kind of spatial characteristics of sound fields. And here we are sort of essentially relying on the same techniques as people are using in measurements, but doing it in the simulation domain, which is, comes with some benefits, such as signal to noise ratios are less of a problem in simulation than in reality and things like that. I have a benchmark around this I'll show you in a second, which is kind of brand new work coming out of Treble. So I'm very excited about that. And then last thing I wanted to mention is the sort of rendering part itself. So we can do these listening experiences in our web tool, which I'll show you in the end. We can do what's called 3-degree of freedom polarization, meaning that you can freely move the head in real time, and the sound field kind of updates with that in real time, but you cannot move around the space. You can just jump between some predefined listening positions, but that's still quite good for many use cases. Of course, it's cooler to have it be even more interactive, where you can walk around freely. That's typically called 6-degree of freedom polarization. And we have sort of a prototype of that. I'll show you one demo of that also, where you can actually be walking around your virtual domain. And then what we have done is we have kind of simulated the spatial impulse response in a grid across the domain. And then and this is done in an offline stage beforehand. And then during runtime, we kind of walk around the domain, and there's some fancy interpolation taking place between nearest impulse responses and kind of spatial audio decoding happening in real time as well. Okay, let me show you a few benchmarks and then move over to a quick demo as well. This first benchmark is just considering our wave solver, where we have this is taken from a database called the Benchmark for Room Acoustic Simulations, which is a collection of various measurements, both from sort of rather controlled scenarios like the one we're seeing here, over to sort of more open-ended or complicated scenarios. Here we have a sound source that emits a wave, which hits this complex surface and is reflected back, and also there's a direct component as well. And if we look at first here on the left, sort of you doing a wave-based simulation on this, we see that we can capture the transfer function between the source and the receiver in a very precise manner. This is not unique to DGFEM. If you have a wave-based method that can capture complex geometries, then you will get a result like this. But if you use geometrical acoustics tools to try and model this kind of surface like this, then they don't really handle this kind of scenario very well. This is from a paper by the authors of the database, where they tried some different commercially available and I think academic tools, which are based on geometrical acoustics, trying to simulate this scenario. And we can see that all of them kind of struggle with capturing this diffraction and the kind of complex geometry that we see in a case like this. Okay. Oops. Second case here is somewhat similar, but then we have a sound source and this kind of free floating plate in space. We have a microphone here, either behind the plate or kind of next to the plate. So it's kind of simulating diffraction around the panel like this, finite sized panel. If we first turn our attention here to the graph on the left, then the microphone in this case is placed behind the panel, so there's no direct line of sight between the source and the receiver. And then we see, as one would expect in a wave-based simulation, that sort of a general trend of the measurement is captured. This kind of shadow effect of the panel at higher frequencies is observed in the simulation too. If we move the microphone so that there is a line of sight between the source and the receiver, then we will see a more sort of oscillatory nature in the frequency response, because you will have a direct component and then some kind of diffracted components from the panel. And we see that both in the simulation and in the measurement that this happens, but we also see that the simulation is not exactly hitting the sort of right dips and peaks of the response. This is probably due to some uncertainty relating to exact positions of the source and the receiver in this setup. Okay. Moving on to sort of a bit more full room simulation. A rather simple scenario though, but still a shoebox room with one surface that is kind of absorbing. There's a porous material that is kind of covering this surface here. Actually tried two different types of absorbers, different thicknesses and flow resistivities, and the rest of the surfaces are hard. This type of scenario is actually, although it might seem simple, and it is simple in some sense, but it's also something that's quite difficult to model accurately. Or we've sort of seen that many practicing acoustic engineers, they complain about that when they're designing, for example, small meeting rooms and things like that, then their current simulation tools really struggle with these types of scenarios and these kind of flutter echo scenarios and so on. Here again, we're still just considering the wave solver, kind of focusing on low frequency behavior. And then for this rather controlled scenario, we see that for both these absorber types, for sort of randomly selected source and receiver position, the measurement and the simulation align up really well. Okay, moving on to a bit more complex room with also some more uncertainty regarding the material properties. So here, in the other one, we kind of knew the flow resistivity of the absorber and so on, whereas here it's a bit kind of less known exactly what the material properties of these surfaces are. And the authors of the database kind of tried to do some in situ measurements of absorption properties, but they also acknowledge that there's kind of various limitations with those approaches and so on. And now we consider first, a low frequency response, considering the uncertainties associated both with the materials and the kind of geometry of the model and so on. I would argue that this is a rather fair match between simulations and measurements at low frequencies. But if we consider the more broadband, now we're simulating with the wave solver up to 3 kilohertz, and then the remainder of the spectrum is done with geometrical acoustics. And we see a sort of fair match between measurements and simulations. This is the narrowband frequency response. This is 1/3 octave band averaged, and this is the phase response. Discrepancies here at high frequencies might be explained by the fact that the measurement is done with a directional sound source, but we actually did this test case with an omni sound source, so we need to update our simulations in this case. And how we're doing on time. Okay, it's okay. Energy decay curves for these different for this room at different frequencies, rather fine match between the two. And if we look at some parameters, then we see a rather good match between measurements and simulations, all things considered. And finally, here for this case, look at time domain response, and we see so the direct sound arrives here. Then according to the sort of 3D model that the authors of the database provide, then the first reflection from the ceiling should arrive here. And sorry, maybe this is the floor and this is the ceiling, either way. but actually in the measurement, those don't add up exactly at the right time. So kind of indicating some slight uncertainty with source and receiver positions again, and acoustic center of the source, etc. But of course, the simulation kind of perfectly matches the expected time. There's kind of less complications in the simulation world, but overall, we see sort of the trend of the time domain response is matching quite well between measurements and simulations. Okay, few comments about the computational performance. So for this particular room we just saw, which is around 150 cubic meters, the runtime will vary depending on how high in frequency we go with the wave solver. There's kind of no way around that. So it kind of grows with frequency to the power of 4. That's kind of just something that we have to live with. But what we can do and is to kind of change that. It's kind of runs, the runtime follows, let's say, C times f to the power 4, and this constant C in front, that's what we can play with and try to get that constant as low as possible. Yeah, we've managed to do that, but still we see this trend. Obviously, as we go higher in frequency, the compute time run grows quite drastically. But the wave phenomena in a room like this is maybe the most prominent in this frequency range here, and that we can do in a very acceptable runtime. If we do want to go to a larger space and or to a higher frequency, meaning a larger simulation problem, more mesh elements, then because this scales so nicely, this continuous Galerkin method, then we can essentially get great performance even for bigger problems by using more compute resources. Of course, there comes a price to that, but sort of at least time-wise, we can do that. So let's say, for example, that we wanted to simulate a 1500 cubic meter room, so 10 times bigger to the same frequency. Then we could use 10 GPUs instead of 1, and we would roughly get the same runtime as we got here with a single GPU in this smaller room. Because of this, what's shown here is called weak scaling efficiency of the solver. As we increase the problem size, but also add more GPUs, how does the performance stay? Like in the perfect world, it should be equal to 1, but it's very close to 1. Okay. This is a quick demo where we used the solver to simulate an HRTF. I think this is mostly kind of illustrating that, with these unstructured mesh methods, we can capture these kind of detailed geometric features like the pinna shape of the ear and model this rather precisely. Here we're kind of comparing the Treble solution to a commercially available finite element tool, and we see a fair match between the two, whereas the Treble simulation, because of this cloud and parallel simulation technology, we could simulate maybe 100 times faster than the traditional finite element solver could. Phase response here as well. Okay, this is the last benchmark here I want to show you. This is kind of maybe most recent work from some of my colleagues. So here we're trying to capture the sound field in a simulation, in a wave-based simulation with a kind of high precision of the spatial characteristics of the sound field. So we can, for example, generate very accurate binaural room impulse responses. In smaller rooms, we can do a fully wave-based simulations without problems, and then create, either, as I said, either do these accurate binaural renderings or do some sort of detailed analysis of the spatial characteristics of the sound field. And so we've built up this whole kind of tool chain of capturing the sound field in a kind of with lots of microphones, like virtual microphone array, encoding that to ambisonics, high order ambisonics, something like 16th order ambisonics, and then decoding that back to a binaural signal or device related signal. And just to kind of validate this chain, let me show you an example here. So the thing that we're testing here is that we have a measurement where we have a kind of a plane wave hitting an HRTF like a dummy, and we record the sound pressure at the two ears, and then we have this kind of HRTF for this given incidence angle here. what we would like to do is to replace having the dummy itself in the simulation, because that's kind of both computationally difficult, because then we need to have very small elements to capture the details of the pin, and it's also kind of unflexible, because if we want to move the head and so on afterwards, we would rather, we can't really do that if we just place the head in the simulation. So rather we would capture the sound field with a virtual microphone array, and then in post-processing afterwards, we can kind of decode that to binaural signals and rotate and everything in real time. So we kind of, in this test case, compare a measurement with, of an HRTF versus simulating a plane wave, picking that up with a microphone array, encoding to higher order ambisonics, and then decoding with the measured HRTF to the binaural signal, and see how that compares to the measured binaural signal. I hope that made sense. So the process is illustrated here. We have an HRTF for a given angle, or an HRTF data set. We then map that over to the spherical harmonics domain. We also have then the simulated sound field at this given location, picked up with a virtual microphone array, which we also convert to the spherical harmonics domain. We can then do some rotation, and then we mix these two together to get the rendered ear signals. This is an example of what an HRTF dataset can look like once it's been converted to the spherical domain. And we see that sort of the bulk of the energy lies in this region here. So as we go higher and higher in frequency, then we kind of need to support higher and higher order of encoding and decoding of ambisonics to capture this kind of energy of the data set. So we built, so we tried to design a microphone array to be able to capture this, the energy of this thing here. We started with a smaller microphone array. Luckily, in simulations, microphones come cheap, actually kind of free. So we can put more or less as many receivers as we want into the simulation without adding much compute cost. So we started here with a 150 mic, 146 mic array, which is kind of enough to go to 8th order ambisonics. Tried a couple of different radiuses of the microphone array. It's a spherical array of cardioid receivers, an open array. And then we see that there's a kind of some region where we think we can, can model very precisely, and other regions where we cannot. So given if we want to cover the full bandwidth up to 8 kilohertz, and this is not good enough, we can extend the bandwidth by reducing the radius of the virtual array. But then we're kind of hurting a bit this sort of low mid-frequency performance. We're still not getting kind of high enough, as we saw here in the slide before, where a lot of energy is for this HRTF dataset. So we ended up designing an array which consists of 434 virtual microphones, and then we have this kind of nice green region here, and which sort of covers the bulk of the energy for this particular HRTF. And then if we do the simulation of either having, if we do the simulation with just having the microphone array in there and not having any kind of dummy, and then compare that to the measured binaural signal, then we see a very good match between the two, and we think this is super cool. Okay. That was it for the presentation. I see time is flying. We'll do 2 minutes of demo of the product, of the beta version, and then let's do questions. So here it's a web-based tool. So I come into the tool just by going to a particular website. Kind of the projects I've been working on here. I'm just going to quickly open one since time is kind of flying. So in here, I have my 3D model, which kind of is live linked to my SketchUp model. I can assign different acoustic materials on different surfaces that I've kind of categorized into different layers when I prepared my 3D model. Can look at details about the materials like the absorption coefficient and the complex reflection coefficient, which is used when modeling the surface. Add my own materials, etc. I can place sound sources and receivers, both directional and omnidirectional sound sources. and some settings, for example, how high in frequency I want to go with the wave solver before I switch over to this geometrical acoustic solvers. And I ran a couple of simulations here beforehand. One thing which we think is pretty cool is that you can kind of run as many simulations as you want in parallel, and you can, once you send off a simulation, then you can just immediately start preparing the next simulation. You don't have to wait for the other one to be finished or anything like that. But because time is kind of limited, before this, I ran a couple of simulations of this classroom, one where the ceiling was hard, like a gypsum ceiling, and one where there was an absorbing ceiling. And we can just quickly look at the results of that. We can kind of compare different results of simulations here, and then I will see, the rear of time is obviously longer. So this is kind of without acoustic ceiling, with acoustic ceiling, something like this. And I can see, obviously the rear of time gets shorter as we when we add an acoustic ceiling, and things like speech intelligibility will increase with having an absorbing ceiling. And I can look at some charts and impulse responses, frequency responses, and things like this in my analysis. I can also listen to the results here in this, what we call the oralizer. So here I can pull in kind of different simulations that I have run. So these two have kind of different materials, and then I can pick a sound for my sounds. I can have many sound sources and then kind of mix this in real time. But here I'll just play something. This is like an anechoic sound you'll hear first. Hope you're hearing some kind of drum machine playing. And then I can kind of jump into the domain, move around, compare the simulations on the fly, and experience the difference.
Birch canoe slid on smooth planks. Glue the sheet to the dark blue background. A large size in stockings is hard to see.
All right, so that's a 2-minute demo of the beta version. But there are many cool things I didn't get the chance to show you, but it's sort of in a nutshell what it looks like. I think I'll stop talking now so there's some time for questions.